Good morning, good afternoon, good evening, depending when you're watching it. So this is pure chapter 3.1 from year 13. It's sequences and series, the first lesson. So I'm going to have a look at sequences, which are just successions of numbers, essentially patterns. And this is going to be very similar to the nth term from GCSE, with slightly different notation. So we're going to have a look at the general formula for the nth term of an arithmetic sequence, where the common difference is constant between successive terms, and then we're going to have a look at some exam-style questions based on these ideas. So before we get started, you've probably guessed there are some warm-up questions, so here they are. 4 to have a go at. The first couple are throwbacks to chapter 1 of this book, so proof, and chapter 3 and 4 we're going to deduce ourselves this formula here, which is going to be key to not just this session, but the whole chapter 3. So pause the video now, try these on your own, and when you're ready to see the solutions, press play, and I'll guide you through how to arrive at the solutions. Okay, so without further ado, let's have a look at worked example 1 to this warm-up. So this question 1 of a warm-up, this is an adaptation of a past paper question. So you might be asked something very similar to this, in fact. So what we've got here is to prove by contradiction there exist no positive integers a and b such that 9a squared minus b squared equals 49. So we're told how to prove it, we're told it's by contradiction. So the first step here is to assume that there does exist an a and b. Assume there exists an a and b, which are natural numbers. So we can say z plus, which means positive integers, or we could have just said naturals. So assume there exists a, b, where they're integers greater than 0, such that (9a squared minus b squared) equals 49. So this is our setup. Now instead of z plus, we could have also have said natural numbers, because positive integers are essentially the natural numbers. So what can we do with this side? Well, if 9a squared minus b squared equals 49, this is actually a difference of 2 squares. So we can say 3a plus b 3a minus b equals 49. So we've got one thing, 3a plus b, multiplied by another thing, 3a minus b. A and b are integers, so 3a is an integer, and 3a plus b will be an integer, as will 3a minus b. So integer multiplied by integer equals 49. So because a and b are both greater than 0, we can say that 3a plus b is greater than 0. So I'm times a number greater than 0 by something else and getting a positive answer. So therefore, if this is greater than 0, 3a minus b must also be greater than 0. So how does this help us? Well, actually, this is very similar now to GCSE. I'm essentially trying to find two values, in this case 3a plus b and 3a minus b, such that one multiplied by the other gives 49. So what we're doing here, really, in a very dressed up sort of way, is finding factors of 49. So 3a plus b will be the greater value, 3a minus b will be smaller. So we could have that 3a plus b is 49 and 3a minus b equals 1, because 49 multiplied by 1 would be 49. So they're two positive possible factors, 49 and 1. Or what other two numbers would multiply to make 49? Well, we could have 3a plus b is 7, and 3a minus b equals 7. So let's see if these have any valid solutions. So we can add these two together. So 3a plus 3a gives 6a, the b's will cancel. 49 plus 1 gives us 50. Therefore a would be 50 over 60, which is 25 over 3. And then if we had that, then we could work out b. So if a were 25 thirds, 3a would be 25. 25 minus what gives us 1, b would be 24. But of course, we're wanting positive integers. 25 over 3 is not an integer. If we look here, add these two together, we get 6a equals 14. Therefore a will be 14 over 6, which gives us 7 thirds. So b, if I sub this a into this bottom equation, 3a would be 3 times 7 thirds, which gives 7. 7 take away b is 7, so b would have to be equal to 0. So in this case, but 7 thirds and 0, they are not positive integers. So whichever way we go, this one or that one, there's no set of positive integers that solve this equation. It fails in this case because 25 thirds isn't an integer, and it fails here because 7 thirds and indeed 0 aren't positive integers either. So therefore, there are no two positive integers a and b such that 9a squared minus b squared equals 49. So prove it by cases. It fails in this case and it fails in this case. It just cannot be done where a and b are positive integers. Let's have a look now at warm-up question 2. We're now told again to prove by contradiction that the square root of 1/3 is irrational. And we're told here that we might be able to assume that if n squared is a multiple of 3, then n is a multiple of 3 too. So we don't need to prove that within this proof. We can assume that if n is a natural number. So again, because of proving it by contradiction, we can assume that the square root of 1/3 is rational. So therefore what we're going to do is we're going to let the square root of 1/3 equal a over b, where a and b are both integers and a over b is a fraction in its simplest form. So in other words, a and b have no common factors. So this is how we set it up in order to prove it by contradiction. So therefore, the square root of 1/3 equals a over b. So next, we can square both sides. And if we do that, the square root of 1/3 gives us 1/3, and a over b squared gives a squared over b squared. Then if we cross multiply, we can see that 1 times b squared equals 3 times a squared. So b squared equals 3a squared. So what we've got here is b squared is a multiple of 3. Which we can now use in our proof. We can use this because we're now told that if b squared is a multiple of 3, we can use the fact that b itself will be a multiple of 3. So therefore, b is a multiple of 3. So now we can introduce a representative for b. So we can let b equal some multiple of 3. So let b equal 3k, where k is a natural number. So now we're just going to sub in that b is a multiple of 3. So let b equal 3k. So if we sub that into here, then we're going to get 3k squared equals 3a squared. So 3k all squared is 3 squared, which is 9, k squared, which is k squared, so 9k squared equals 3a squared. Now if I divide both sides by 3, I get a squared equals 9k squared over 3, which is 3k squared. So now I have, so a squared as well. A squared is a multiple of 3. In the same way as what we proved for b, we've now proven that a is a multiple of 3 by the same logic. So a is also a multiple of 3. So now, so a and b are multiples of 3. Hence, because of this fraction here, a over b, that is never going to be a fraction in its simplest form. Now, of course, any fraction can be written in its simplest form. Any fraction has a simplest form. So what we're saying here is that this is a fraction which exists, which can never be in its simplest form, which is an absolute nonsense. And if you've got a fraction that can't be simplified, it's not a fraction at all. So we've shown that because a and b have to be multiples of 3, a over b can never be represented as a fraction in its simplest form if this were true. So if this were true, we end up with a nonsense, which can never be the case. We've followed it through carefully and logically, and not made any mistakes with our reasoning. So the only conclusion is our initial assumption must have been false. So therefore, root 1/3 must actually be irrational. So therefore, the square root of 1/3 must be irrational. Let's have a look at warm-up question 3. Now I've made a claim here to use this strategy I've shown you here, so don't be thinking about how you find the nth term. This idea is important, trying to prove the general A-level version of the nth term of an arithmetic sequence. So the nth term, which we're going to call u subscript n, for any linear, which is another way of saying arithmetic sequence, can be expressed in relation to the first term a and the common difference d. So it's shown in this following example. So 3, 7, 11, 15, 19. We're going up in 4s. The first term is 1 less than 4, you might be thinking. So it's just 4n, then minus 1, because this 3 is 1 less than what it's going up in, which is 4. But please think of it like this. It's going up in 4s, so put that number followed by n, and then we get the minus 1 by considering the first term minus the common difference. 3 minus 4 gives us the minus 1. So think of it like this if we can for these two examples. So here, 7, 9, 11, 13, 15. So we can see here that the common difference is 2. The values in this sequence are increasing by 2 each time. So here I can say it's 2n. And then this 7 differs by 2, of course. So it differs because the first term 7 is 5 higher than the 2. And we get that 5 by taking this first term 7 and subtract the 2, which gives us 5. So un is going to be 2n plus 5. In a similar way for this one, the common difference is 7. Let's go up in 7s. So we've got 7n, and this 1, we've got 1 minus what it's going up in. 1 minus 7 gives minus 6. So this un is going to be 7n subtract 6. So now we're going to generalise this for warm-up part 4. So for warm-up part 4, we've got this generalised arithmetic sequence. So first term's a, common difference is d. So these terms are going up by d each time. Add d to a, we get a plus d. Add d to this gives us a plus 2d, then a plus 3d, and so on. So using what we had before, this one here is going up in d each time. So I'm going to use exactly the same idea as question 3. So for this one, we've got un, so it's going up by d each time. So we've got d followed by n. Now what we're going to do is take this a and then subtract it from the common difference. So a, then we subtract the common difference from that. So then we have a minus d, just like we had in question 3. So rearranging that, we've got a plus nd minus d. So we've got a, and if we factorise out the d here, we've got n minus 1 lots of d. So we've got a plus d, brackets n minus 1. Rewrite this slightly differently, so it's in this particular form. We've got a plus n minus 1 lots of d. And this is going to be central to this subchapter. So hopefully now we're warmed up, let's have a look at the general theme of this lesson. So we've just proven the general rules of the nth term of an arithmetic sequence. So we've just deduced, like I've said in the warm-up, question 4, that the nth term, un, of an arithmetic sequence is a plus n minus 1 multiplied by d, where a is the initial term, the first term, and d is a common difference between consecutive terms in the sequence. So let's use this in a few worked examples, followed by you trying some questions independently. So, worked example 1. We have the nth term of an arithmetic sequence, which is un is 55 minus 2n. First of all, we need to write down the first 5 terms. So I'll just section this out like so. So for the first 5 terms, we can do this very quickly or slightly slowly. I'll do it the slow way, just so it's absolutely clear, or touch wood, it's really clear. So first 5 terms, well, the first term will be u1. That's 55 minus 2 times 1, which is 53. u2, apart from being a band, that's 55 minus 2 times 2, which will be 51. u3, 55 minus 2 times 3, which is 49. u4, 55 minus 2 to the 4, you've got the idea by now, I'm hoping, that's going to be 47. And finally u5, 55 minus 2 to the power 5, which is 45. So the first 5 terms are just 53, 51, 49, 47 and 45, and you may have been able to have done that without even doing this step here. So it's going down in 2s, so 55 take away 2, 53, then 51, and so on and so forth. So this is very much GCSE, but just dressed up a little bit. B for 99th term. So for B, 99th term means n is 99. So u99 is 55 minus 2 lots of 99. So we just need a calculator to do this. Well, we don't need one, but a song is just using one. So 55, subtract 2 lots of 99, that gives us minus 143. And for part C, the first negative term, well, it's going to be negative when un becomes less than 0. So we set 55 minus 2n, which is un, to be less than 0. Add 2n to both sides. We have this. Divide by 2. So therefore the smallest n which satisfies this is going to be 28, because n is always going to be a natural number in a sequence. A sequence number is either the first, the second, the third. So n has to be a natural number. The smallest natural number satisfying this has to be therefore 28. So therefore n is 28. So therefore u28 is 55 minus 2 lots of 28, 55 minus 56. So the first negative term is minus 1. So that's the first one done. Let's have a look at worked example 2. This one here, we have a sequence which is generated by this formula: u subscript n is an plus b, where a and b are constants to be found. We're told that the fourth term, u4 is 19, and the 10th term is 43. Find the values of a and b. So using this idea first, that u4 is 19, that tells us that 19, move this down here in fact, so 19 equals a times 4, 4a, plus b. Just using the fact that the fourth term is 19. Whereas the 10th term, U10, is 43. So we have 43 equals A times 10, 10A, plus B. So now what we have is actually a very simple simultaneous equation to solve. And so what we need to do here is just one subtract the other. So if we just subtract the top from the bottom, 43 take away 19 gives 24, 10A take away 4A gives us 6A, and the B's cancel. So 24 equals 6A, therefore A equals 4, which we now sub in back into either the blue or the yellow. So if we sub this into whichever one you think, I'm going to go for 19 equals 4A plus B. We have 19 equals 4 times A, so that's now 4 times 4 plus B. So 19 equals 4 times 4 is 16 plus B. So therefore B is 19 take away 16, B is 3. So we have that UN is A times N, so that's going to be 4 times A. Sorry, 4 times N, apologies. A is 4, so 4N plus 3. So that's that one done. So A is 4, B is 3. That's the sequence. Let's have a look at one more, and then it's over to you to try some. So the first three terms of an arithmetic sequence are 4k plus 5, then 5k, and finally k squared. Find the values of k, or value, hence determine the nth term of a sequence or sequences. So the hint here, there might be more than one value of k. So it's an arithmetic sequence. This tells us that the common difference is constant. So from 4k plus 5 to 5k, that must be a difference of d. And from 5k to k squared, again must be a difference of d. So the common difference is d. So therefore, the difference between 5k and 4k the difference between 5k and 4k plus 5, to look at the difference, it's one subtract the other. So 5k minus 4k plus 5 must be the same difference as the difference between k squared and 5k. So all we're doing here is using this idea of common differences. So the difference between 5k and 4k minus 5 is the same as the difference between k squared and 5k before it. So let's simplify this. 5k minus 4k plus 5, that gives us k minus 5. Over here we have k squared minus 5k. If we now subtract k minus 5 from both sides, so we get 0 on the left equals k squared. If I subtract a k, that gives me minus 6k, and minus 5 gives me plus 5. You should see now that this will factorise. So two numbers that multiply to 5 add up to negative 6. That's negative 5 and negative 1. So therefore k equals positive 1 or positive 5. So they're the two values of k. K is 1 or k is 5. But now we need to find the nth terms of each. So let's start off first of all with k being equal to 1. So if k is 1, then the sequence would be 4k plus 5, 4k plus 5, which is going to be 4 times 1 plus 5, which is 9. 5k will just be 5. K squared is 1 squared, which is 1. So in this case, the first term is A. The common difference, 5 take away 9, or 1 take away 5, is minus 4. So therefore the nth term of this one, if k were 1, would be un equals A, which is 9, plus n minus 1 multiplied by the common difference, so n minus 1 multiplied by minus 4. So n times minus 4, that's going to be minus 4n, minus 1 multiplied by minus 4 is plus 4, so 9 plus 4 gives 13. So that would be the nth term if k were 1. So if k were 1, we'd have that un equals 13 minus 4n. Whereas if k were 5, and I think I might just color code this slightly differently. So if k were 5, then the first term, 4k plus 5, would be 4 times 5, which is 20, plus 5, which is 25. 5k would be 5 times 5, which is 25. And k squared would be 5 times 5, which is 25. How peculiar. Now, this might throw you off slightly. This is like, is this a sequence? Well, actually it is. It might be one of the world's most boring sequences, but it is an arithmetic sequence because it has a common difference from one to the next. The common difference here just so happens to be 0. So in this case, A is 25, first term 25, common difference is 0. So in this particular boring case, you could have that un is just 25 each and every time. So it's very unlikely to give you one where the common difference is 0, but I wanted to include that example just so you could see that it is potentially something which would be a sequence, albeit barely a sequence worth mentioning at all. It's the most boring sequence I could think of, but there you go. So here, if the sequence wasn't a trivial sequence, we'd have it where the case was k equals 1. But these worked examples should set up enough of an idea to give you a grounding to try some questions on your own. So, in your books, if you could turn to page 61, exercise 3a, and try these question parts. Question 1 AC, 2 ACE, 3 BDF, 5, 6, and 8, 9, and 10. Feel free to try more questions if you can, of course, but these should give you a good grounding of the ideas moving forward. As ever, every time you try a question, be sure to self-assess and make sure you're on the right tracks before moving on to the next questions. If you are stuck, ask a classmate or me in class, or if failing that, please email me. You can even leave a comment in the video. I hope you found that useful, so do feel free to subscribe, and I hope to see you all soon. So once again, I'll bid you goodbye for now.